Detecting faults in steel plates is crucial for maintaining safety and reliability. This study proposes a novel approach using machine learning techniques, specifically the fitness-dependent optimizer (FDO) and neural networks, to diagnose and predict the likelihood of faults in steel plates based on experimental text data. The research compares the performance of various machine learning models, including Gray Wolf Optimizer (GWO), based in FDO-based multi-layer perceptron (MLP), and cascaded MLP (CMLP), to classify steel plates as either faulty or non-faulty. The results show that all models yielded promising outcomes, with the FDO-based MLP and CMLP models consistently achieving 100% accuracy in all tested datasets. These findings suggest that models employing the FDO as a learning algorithm have the potential to achieve higher accuracy, albeit with a slightly longer runtime compared to other algorithms. The study highlights the critical importance of early fault detection in steel plates, which can significantly affect their quality and ability to withstand corrosion and wear. Surface defects in steel products can significantly impact their quality, emphasizing the need for effective predictive diagnosis methods. This research demonstrates the potential of machine learning techniques to accurately predict and diagnose faults in steel plates. The approach has significant implications for improving inspection systems used in steel production, enhancing product quality, and reducing potential risks associated with faulty steel plates. Detecting surface defects on steel plates is a crucial task in quality control, particularly under varying lighting conditions. To accomplish this, defect identification algorithms analyze images and categorize surface defects. However, designing effective algorithms for surface defect detection and classification is challenging due to the rarity and variations in appearance of these defects. Steel plates commonly exhibit two types of surface defects: seams and scales. These defects demonstrate considerable differences within each category, and the image background is often intricate. To address this challenge, 4 distinct approaches have been proposed for surface defect detection: statistical, model-based, structural, and filter-based techniques. The statistical approach utilizes properties such as histogram, autocorrelation, local binary patterns, and gray-level co-occurrence matrix (GLCM) to determine various statistics of texture, including entropy, dissimilarity, energy, correlation, homogeneity, and contrast. The model-based approach involves creating mathematical models to represent surface defects and comparing the actual surface with the models to detect deviations. The structural approach examines the geometric properties of the surface, such as edges and contours, to detect defects. The filter-based approach uses various filters to enhance the appearance of surface defects. Despite the availability of these approaches, there are still limitations that need to be addressed. One significant challenge is the need for specialized illumination and imaging equipment, which can be a constraint in real-world applications. This limitation highlights the need for further research and development to create more robust and adaptable surface defect detection algorithms. The detection of surface defects on steel surfaces remains a significant challenge due to the high cost and difficulty of maintaining traditional inspection methods, as well as the impact of changing lighting conditions and surface geometry on detection algorithm accuracy. Recent advancements in defect detection algorithms have demonstrated improved durability and effectiveness in inspecting steel surfaces. For instance, the use of extreme learning machines, ELMs, and genetic algorithms, GAS, have shown promise in classifying hot-rolled plate defects. Enhanced meta-heuristics can further improve the process. Another approach involves incorporating the RNamlet as a feature extractor, enabling asymmetric image decomposition and enhancing adaptability across various steel production lines. Surface inspection algorithms have also been developed using the scale-invariant feature transform (SIFT) and support vector machine (SVM), demonstrating favorable detection outcomes in production lines with uncomplicated backgrounds. The shearlet transform (STREET) has been employed to offer an effective representation of defects at multiple scales, significantly enhancing precision in defect recognition on steel surfaces with intricate backgrounds. Furthermore, combinations of discrete Fourier transform (DFT) and artificial neural networks, as well as Gabor filters, have been used to detect surface cracks on structural steels and identify corner and thin cracks in raw steel blocks. An online system for crack detection has also been designed, integrating 3D contour data from the steel plate surface with image processing and statistical classification using logistic regression. Despite these advancements, surface inspection algorithms need to possess the ability to classify intricate defects and learn from unlabeled data. Deep learning techniques, such as convolutional neural networks, CNNs, have shown exceptional performance in tasks like image classification and object detection, and have been widely used in recent times. Unlike other classification algorithms, CNNs do not require manual feature engineering, making them a promising approach for surface defect detection. Convolutional neural networks, CNNs, have revolutionized image classification tasks by learning the weights of convolutional layers through minimizing the loss function, eliminating the need for explicit feature extraction processes. This enables CNNs to achieve superior classification results even with complex backgrounds and appearance variations. Variants of CNNs, such as AlexNet, VGG, NIN, Inceptions, Inception ResNet, and DenseNet, have been proposed to extract more nonlinear features by incorporating deeper stacked convolutional layers or employing asymmetrical structures. These advancements have enabled CNNs to tackle more demanding tasks, including object detection. However, the effectiveness of CNN-based approaches heavily relies on the availability of an adequate number of training samples. When training a CNN with small datasets, the algorithm's ability to generalize can be significantly affected, limiting its applicability in industrial settings. Transfer learning, which assumes that sample images exhibit basic characteristics, such as edges and curves, has been employed to utilize CNNs with small datasets for tasks like emotion recognition and automated medical diagnosis. However, in the context of steel surface inspection, the effectiveness of applying transfer learning is limited due to the substantial disparity in image context between steel surfaces and pre-existing models. This violates the application requirements of transfer learning. Despite this limitation, machine learning techniques have shown promising results in diagnosing and predicting faults in steel plates. The use of various machine learning algorithms, such as MLP and CMLP optimized with GWO, MGWO, and FDO, has demonstrated the potential for accurately classifying steel plates as either faulty or non-faulty. Notably, FDO_MLP and FDO_CMLP consistently achieved 100% accuracy in all tested datasets, suggesting that using the FDO algorithm as a learning algorithm may lead to higher accuracy with a slightly longer runtime compared to other algorithms. These findings highlight the importance of early detection of faults in steel plates for maintaining safety and reliability and the significant role that machine learning techniques can play in achieving this goal. This comparative study employs a distinct machine learning methodology to assess the performance of 5 different models in classifying steel plate faults. The dataset used is a unique steel plate fault dataset from the Research Center of Sciences of Communication in Italy, comprising 6 fault types: pastry, Z-scratch, K-scratch, stains, dirtiness, and bumps. The dataset consists of 29 variables, including minimum and maximum X and Y coordinates, pixels areas, X and Y perimeters, sum of luminosity, and various indices related to steel plate properties. The methodology involves data collection and feature selection, where the 29 variables are carefully chosen to represent the steel plate faults, ensuring that the dataset is diverse and informative. The dataset is then prepared for modeling by applying appropriate pre-processing techniques to ensure data quality and consistency. The 5 machine learning models with distinct architectures or training algorithms are then applied to the prepared dataset, and their performance is evaluated using statistical techniques. The outcomes of each model are compared to determine the most effective approach for steel plate fault classification. This comparative study aims to identify the most suitable machine learning approach for steel plate fault classification, providing insights into the strengths and limitations of each model. The results of this study will have implications for the development of efficient quality control systems in the steel manufacturing industry. In the realm of machine learning, pre-processing data for model training is a crucial step. Positive and negative input features are encoded as 0 and 1, respectively, with the target represented by 1 for positive and 2 for negative. This paper delves into the methodology of classification models, focusing on neural network architecture and training methods. The neural network architecture consists of 3 key components: the total number of layers, the presence and quantity of hidden layers, and the number of nodes within each layer. The optimal topology for a neural network is determined by regulating the number of hidden layers and neurons within each layer. In this study, a single hidden layer is utilized, and the number of neurons in that layer is determined by the number of features present in the dataset. The criterion for determining the number of neurons in the hidden layer is given by equation 1, where HNO represents the number of hidden layers and ENO represents the number of input layers. 2 types of neural networks are employed: basic feedforward artificial neural networks, ANNs, and cascade feedforward ANNs. The basic ANN consists of 3 interconnected layers: an input layer, a hidden layer, and an output layer, where the network establishes connections from the input layer to each subsequent layer and between each layer and the subsequent ones. In contrast, the cascade ANN introduces an additional connection that directly links the input layer to the output layer, allowing the network to learn intricate associations and enhancing the speed at which it acquires the desired relationship. This is supported by previous studies, 35, 36, which highlight the benefits of incorporating additional connections in neural networks. The artificial neural network training process aims to determine the optimal weights and biases that yield the highest possible accuracy in classification. To achieve this, various models employ optimization algorithms, including the Gray-Wolf optimizer, modified Gray-Wolf optimizer, or fitness-dependent optimizer. These algorithms adjust the weights and biases to minimize an associated objective function, typically the mean square error, MSE, in neural networks. The MSE, calculated using equation 2, quantifies the average squared difference between the desired output and the output generated by the ANN model. It is defined as the sum of the squared differences between the desirable output, y, and the achieved value, y caret, across all input unit iterations, I, and number of outputs, n. To assess the model's performance, the MSE is computed for all training samples and then averaged using equation 3. This average MSE value is utilized by the optimization algorithm to make adjustments to the weights and biases of the model, aiming to minimize the average MSE across all training samples. Figure 3 illustrates the optimization process, demonstrating how the algorithm adjusts the weights to minimize the mean square error and achieve optimal performance. The application of the optimization algorithm to update the weights of the neural network and achieve maximum accuracy is a critical step in the training process. The proposed models employed 2 primary evaluation approaches for training procedures: the mean square error, MSE, value and the confusion matrix. The MSE value signifies the model's effectiveness, with a lower value approaching 0 being desirable. The confusion matrix provides a summary of accurate and inaccurate predictions, enabling the calculation of sensitivity, specificity, positive predictive value, PPV, and negative predictive value, NPV. These metrics measure the reliability of the model, providing insights into the probability of true positive and true negative classifications. The optimization algorithms utilized in this research include the standard and modified Gray-Wolf optimizer, as well as the fitness-dependent optimizer. These algorithms are used to find the most suitable weight and bias values for a neural network, which is crucial for predicting the presence or absence of a specific condition based on the input data. The optimization process aims to minimize the error between the predicted and actual outputs, thereby enhancing the model's accuracy and reliability. The evaluation of the applied models involves a comprehensive analysis of their performance metrics, including sensitivity, specificity, PPV, and NPV. These metrics are derived from the confusion matrix and provide a detailed understanding of the model's ability to correctly classify samples. A value closer to 1 for these metrics indicates a more favorable result, with an optimal outcome represented by a value of 1 and the poorest performance indicated by a value of 0. The use of optimization algorithms in this research is critical for fine-tuning the neural network's parameters to achieve optimal performance. By employing algorithms such as the standard and modified Gray-Wolf optimizer, and the fitness-dependent optimizer, the model can be optimized to minimize the prediction error and improve its overall reliability. This optimization process is essential for enhancing the model's predictive capabilities and ensuring that it can accurately identify the presence or absence of the target condition in new, unseen data. The application of optimization algorithms in detecting the absence of faults in steel plates is a pivotal area of research. This section delves into the use of gray wolf optimization, GWO, a swarm intelligence algorithm inspired by the hunting behavior of gray wolves. The social hierarchy within a wolf pack forms the basis of this algorithm, where the alpha represents the most preferred solution, followed by beta, delta, and other solutions classified as omega. During a hunt, gray wolves first encircle their prey, and the position of the gray wolf, T, around the prey, T, is updated using the equation D equals C T. This equation represents the distance between the gray wolf and the prey, which is crucial for the optimization process. The GWO algorithm's efficiency in hunting is mirrored in its ability to efficiently find optimal solutions in complex optimization problems. The use of GWO for fault detection in steel plates leverages its capability to navigate through the solution space, identifying the absence of faults effectively. The algorithm's reliance on swarm intelligence allows it to explore multiple potential solutions simultaneously, increasing the likelihood of finding the optimal solution. A figure illustrating the position vectors in two-dimensional space provides a visual representation of the optimization process, demonstrating how the gray wolf's position is updated relative to the prey. This visual aid helps in understanding the algorithm's adaptability and efficiency in solving complex problems. In summary, this section highlights the application of gray wolf optimization for fault detection in steel plates, emphasizing its potential as an efficient tool for solving complex optimization problems. The gray wolf optimization algorithm, a nature-inspired optimization technique, is employed to locate the optimal solution in complex problems. This algorithm simulates the hunting behavior of gray wolves, where alpha, beta, and delta wolves are assumed to have better knowledge of the prey's location. The positions of these three wolves are preserved, while the remaining wolves update their positions based on the saved solutions. The algorithm utilizes coefficient vectors represented by A and C, which are defined using equations. These vectors are used to update the position of the wolves, with the alpha, beta, and delta wolves guiding the search process. The position of the current solution is updated based on the distances between the alpha, beta, and delta wolves, as calculated by equations that represent the distances between these wolves and the current solution. The algorithm iteratively updates the positions of the wolves until the optimal solution is found. The components of the vector A decrease linearly from 2 to 0 over iterations, allowing the algorithm to converge towards the optimal solution. The random vectors R1 and R2, ranging between 0 and 1, are used to introduce randomness in the search process. The gray wolf optimization algorithm is a powerful tool for solving complex optimization problems due to its ability to balance exploration and exploitation. By mimicking the cooperative hunting behavior of gray wolves, this algorithm can efficiently search the solution space and locate the global optimum. The gray wolf optimizer algorithm plays a crucial role in the proposed methodology, with its parameters controlling exploration and exploitation. The position of the wolf pack is updated based on the alpha, beta, and delta wolves, with the C vector serving as a key parameter that regulates the level of difficulty in reaching the prey. A value greater than 1 increases the challenge, while a value less than 1 makes it easier, thereby preventing local optima. The A parameter facilitates exploration, with its value determined by a linearly decreasing parameter ranging from 2 to 0. When the random A values fall within the 1 interval, a wolf can move to any position between its current location and the prey's position. If A less than 1, the wolves launch a direct attack, while values greater than 1 signify an attack from a distance. To modify the gray wolf optimizer, 2 changes are proposed. Firstly, a new group of wolves, gamma, is introduced, in addition to the existing alpha, beta, delta, and omega groups. This enables the omega wolves to adjust their positions based on all 4 groups, rather than 3. Secondly, the equation for determining the step size of the omega wolves is modified to include an extra equation, computing the distance between the alpha, beta, delta, and gamma wolves, denoted by d gamma equals C4 x gamma x. This enhancement enables the GWO algorithm to escape local optima more effectively, thereby improving its exploration capabilities. In the gray wolf optimizer (GWO) algorithm, the calculation of alpha, beta, delta, and gamma positions is crucial for guiding gray wolves towards potential prey. These positions are computed using specific formulae that incorporate the current solution and the average of the three best solutions, ultimately updating the position of each gray wolf in the pack. In contrast, the fitness-dependent optimizer (FDO) algorithm, introduced in 2019, draws inspiration from the reproductive behavior of swarm bees. This algorithm consists of two primary components: the search process and the movement process. During the search process, scout bees act as search agents, seeking new solutions. In the movement process, the position of a scout bee is updated. The FDO algorithm initiates with the generation of initial positions for artificial scout bees within the search space. Throughout its execution, the algorithm maintains a global best solution, ensuring that the optimal solution is continually refined. By leveraging the collective behavior of swarm bees, the FDO algorithm efficiently explores the search space, yielding improved optimization results. In the FDO algorithm, scout bees employ a combination of fitness weight mechanisms and random walk to explore and discover new solutions within predefined boundaries until the end of the process. They persistently search for improved solutions, and if a superior solution is discovered, the previous solution is discarded in favor of the new one. If no better solution is discovered, the previous solution is retained. The movement process of the scout bee involves updating their positions to improve the solution, as denoted by equation 11, where T plus 1 represents the updated position of the scout bee, T is the current position, and pace denotes the speed and direction of movement. The pace's speed and direction are influenced by the fitness weight, Fw, which is computed using equation 12, as the absolute difference between the best global solution and the current solution, normalized by the weight factor, Wf. The weight factor, Wf, controls the fitness weight, determining the movement pace of the scout bees in FDO. The value of Wf can be either 0 or 1, with 1 indicating a high level of convergence and a low chance of coverage. However, if Wf is 0, it is ignored and does not affect the equation. To avoid unacceptable cases, the Fw value should be between 0 and 1, and the equation should avoid division by 0, which can occur if the value of T's fitness is 0. The rules, as shown in equation 10, are applied in FDO to ensure that the search process is stable and effective. The proposed equation 13 outlines the mathematical framework for the optimization process in a machine learning classification model. This equation utilizes a randomly generated number, denoted as r, within the interval 1, 1, to adjust the position of a search agent in the solution space. The current solution at iteration t for search agent I is represented by T, while T denotes the best solution achieved globally up to the present moment. This optimization process is crucial for the proposed model, as it aids in determining the optimal parameters that maximize the classification accuracy. The implementation, results, and discussion section of the paper focuses on the outcomes achieved through the implemented architecture. The construction and execution of the machine learning classification model were conducted using the MATLAB platform. To evaluate the classification model, a dataset was utilized and divided into an 80-to-20 ratio, with 80% of the data used for training purposes and the remaining 20% reserved for testing. Tables 1 and 2 present the classification accuracy of each model on the dataset, showcasing the performance during the training and testing phases of the implemented architecture. The datasets were divided into training and testing sets using an 80-to-20 ratio, comprising a total of 1,941 samples, with 1,553 samples allocated for training and 388 samples for testing. All models were tested under identical conditions, employing 10 search agents and a maximum iteration of 50 for each algorithm. From Table 1, it can be observed that all models yielded similar results, but the FDO algorithm exhibited a higher likelihood of achieving more accurate outcomes, attaining 100% accuracy across all experiments. However, it is worth noting that the FDO algorithm took longer to complete compared to the GWO algorithm. Notably, the GWO_MLP model demonstrated the shortest runtime, possibly due to the faster GWO algorithm and the MLP architecture having fewer connections compared to the CMLP. This section of the research paper presents a comprehensive performance evaluation of various machine learning models on a dataset. Table 1 outlines the proposed models, detailing their sample sizes, dimensions, runtimes, and classification rates during both training and testing phases. The results demonstrate high classification accuracy ranging from 99% to 100%, underscoring the effectiveness of these models. Table 2 provides detailed performance metrics for each model, including the number of correctly predicted positive and negative cases, accuracy, and mean square error, MSE. These metrics further emphasize the strong performance of the models, particularly in terms of accuracy and MSE. Table 3 offers an evaluation of the confusion matrices for the proposed models, providing insights into their performance. The sensitivity, specificity, positive predictive value, PPV, negative predictive value, NPV, and accuracy are all presented, showcasing the model's capabilities in classifying the dataset. Finally, Figure 5 illustrates the receiver operating characteristic, ROC, curve results of all the proposed models tested on the dataset, visually representing their performance. The ROC curve is a graphical representation of the performance of a binary classification model at all thresholds, thus providing a comprehensive overview of the model's performance. In summary, this page presents a thorough evaluation of the proposed machine learning models, highlighting their strong performance in terms of classification accuracy, MSE, and confusion matrices. The use of ROC curves also provides a visual representation of the model's capabilities, further emphasizing their effectiveness on the dataset. Early fault detection in steel plates is crucial for ensuring safety and reliability. To address this, 5 machine learning techniques were employed to classify steel plates as faulty or non-faulty. Meta-heuristic algorithms, such as the Firefly optimization (FDO) algorithm, were utilized to minimize mean square error. The results show that FDO-based multi-layer perceptron (MLP) and cascaded MLP (CMLP) models achieve 100% accuracy, outperforming other models, despite requiring a longer runtime compared to the Gray-Wolf optimization (GWO) algorithm. Although slight variations in performance are observed across different datasets, no significant difference is found between MLP and CMLP models. Notably, the presented classification models exhibit high precision, paving the way for the development of a predictive system for identifying high-risk patients, a critical step in controlling disease spread. By leveraging these findings, early detection and intervention can be facilitated, ultimately enhancing safety and reliability in various industries. Developing highly reliable and efficient systems for steel plate fault classification is crucial in the engineering field, where accuracy is paramount. While achieving 100% accuracy in classification models is rare, factors such as the number of features used and classification ease can influence results. Notably, the current dataset lacks noisy data, which may lead to generalization errors, emphasizing the need for additional testing to ensure model reliability. To expand and develop this research, several future work directions are proposed. Firstly, increasing the database size by incorporating more features and samples related to steel plate faults can enhance the efficiency and comprehensiveness of the prediction process. Secondly, exploring alternative neural network models capable of processing diverse data types, including images, audio, and time series data, can lead to the development of a more advanced system with enhanced intelligence and broad advantages in the engineering field. Thirdly, investigating novel approaches to generate reliable and advanced models is suggested. This can be accomplished by adapting or combining utilized algorithms with traditional or meta-heuristic algorithms to construct innovative models. By pursuing these directions, researchers can develop more sophisticated steel plate fault classification systems, ultimately improving the reliability and efficiency of engineering applications. Steel surface defect detection and classification have garnered significant attention in recent years, with various techniques and methodologies being employed to improve detection accuracy and efficiency. One such approach involves the use of adaptive multiverse optimizer, a nature-inspired algorithm that leverages the principles of universe creation to optimize complex problems. This optimizer is used in conjunction with the shearlet transform, a mathematical tool that provides a sparse representation of signals, allowing for efficient feature extraction and defect detection. Another approach utilizes Gabor filters, which are specifically designed to extract features from images. The filter's ability to capture both frequency and orientation information enables the detection of defects with varying textures and patterns. Furthermore, neural networks have also been employed in steel surface defect detection, with convolutional neural networks, CNNs, being particularly effective in image classification tasks. The combination of these techniques has led to significant improvements in defect detection and classification accuracy. For instance, the adaptive multiverse optimizer has been shown to outperform traditional optimization algorithms in defect detection tasks, while the shearlet transform has enabled the extraction of robust features that are invariant to rotation and scaling. Similarly, Gabor filters have been found to be effective in detecting defects with specific textures and patterns, and CNNs have demonstrated high accuracy in classifying defects into different categories. Despite these advancements, there are still limitations and challenges associated with steel surface defect detection and classification. For instance, the complexity of steel surfaces and the variability of defects can make it difficult to develop a universal detection approach. Additionally, the requirement for large amounts of high-quality training data can be a significant challenge. Future work in this area should focus on addressing these limitations and developing more robust and efficient detection and classification techniques. Please provide the content that needs to be refined. I'll transform it into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth, and following the guidelines you provided.